In the previous video, we obtained graphs of sine and cosine as functions of angle theta expressed in fractions of pi. In this video, we provide two ways to enumerate decimal approximations for pi. The first method involves a formal geometric argument. Construct a unit circle. Arrange three identical triangles. The arc length around the entire circle is 2 pi, but we have chosen our three triangles so that they correspond to a total arc length of only half a circle, or only pi. Since the triangles are identical, each triangle corresponds to an arc length of pi over 3. Because we are studying a unit circle, all radial spokes have length 1. This means that all three triangles are isosceles, and the unlabeled angles are all equal to each other. Because the interior angles of a triangle sum up to pi, these remaining angles must all be pi over 3. Indeed, the triangles are equilateral. To continue our discussion, we enlarge this triangle for a better view. Drop an altitude to divide the top interior angle of pi over 3 into two equal angles of pi over 6. The altitude we have drawn divides the opposing leg into two legs of length 1/2. In this diagram, we label the length of the altitude x. According to the Pythagorean theorem, the square of the length 1/2 plus the square of the length x equals the square of the length of the hypotenuse, which is 1. Isolating x squared and solving for x produces root 3 over 2. Flip the green triangle so that its long leg sits flush with the previous location of its short leg. This arc has a length of pi over 6. Draw a slender right triangle that shares a leg of length 1/2 with the green triangle and which has its hypotenuse touching the pink circle at the beginning and end of the yellow arc segment. The remaining unshared legs lie on a radial spoke with length 1, so the length of the remaining leg of the blue triangle is 1 minus root 3 over 2. We use the letter y to label the hypotenuse of the blue triangle. Applying again the Pythagorean theorem, the sum of the squares of the lengths of the legs of the blue triangle, meaning 1/2 quantity squared and 1 minus root 3 over 2 quantity squared, this sum equals y squared. Placing the difference over a common denominator 2 and simplifying provides an opportunity to pause the video and repeat the last step. We can solve for y, here meant to be a positive length. The yellow arc is a slightly indirect path for connecting the two endpoints of the hypotenuse of length y. Thus, pi over 6 is slightly longer than y. This is the same as saying that pi is slightly larger than 6 times the root of 2 minus root 3. Evaluating the radicals by hand or using a calculator, we find that pi is slightly larger than 3.1. We obtained a numerical approximation for pi by defining pi as half the circumference of a unit circle and then using the Pythagorean theorem to study the lengths of the sides of right triangles. To increase the precision of our approximation of pi, we could draw and analyze increasingly thin triangles. However, rather than cluttering the page, we will reveal a convenient mnemonic for memorizing 6 digits of pi. Sine, sine, cosine, sine, 3.14159. We have just provided two options for enumerating digits of pi. One option was to analyze the geometric properties of triangles formally, and the other was to memorize an entertaining chant. Knowing digits of pi allows us to recognize that labels on the horizontal axis of the plots of sine and cosine are simply numbers that can be approximately expressed using decimal representation. It is helpful to be aware that in some discussions, angles are expressed in terms of degrees. The symbol 1 degree is simply an abbreviation for the ratio pi divided by 180. We have now made a first acquaintance with the concept that sine and cosine are functions associated with the unit circle, and we have presented 3 conventions for labeling the horizontal axis, that is to say, the angle theta, when plotting these functions. In addition to analyzing circles, sine and cosine functions are often applied to study the geometric features of triangles, including of right triangles. Thus, in the next video, we relate sine and cosine to the lengths of edges of right triangles, and we use this perspective to practice deriving a couple of trigonometric identities.